Okay, in the last video we talked about naming molecular compounds, and in this video we are going to focus on naming ionic compounds. So, with ionic compounds, remember they are going to form between a metal and a non-metal. Okay, so you're going to get a metal and a non-metal to form an ionic compound. Okay, and I already drew my bad picture of the periodic table in the last video, so I won't force you to listen to that again. But an ionic compound is going to be the simplest ratio of the compound's anions, which are negatively charged, as well as the cations, which are positively charged. Okay, and just as a reminder on the little picture over down here, your chlorine is your negatively charged anion. They're going to get larger because when you add another electron, it's able to repel the protons a little bit further in the middle. The sodium cation is smaller because it gives away one of those electrons and kind of pulls everything in. And ultimately, the whole goal on these is you want to get the electrode charge of the ion equal to 0. So for example, this would be a 1-to-1 ratio because it takes one sodium ion to cancel out every one chloride ion, and we'll see how that dictates. Now with ions, we should have already looked at our ion sheet at this point and tried to focus on the S and P block elements that form, P block elements that form nice stable ions because they all want to be like the noble gases. They want to, the group 1s will all have a 1 plus, the halogens will all have a 1 minus, etc., based on those valence electron configurations. Now, all elements will easily form ions. Some atoms will form covalent bonds. We see this a lot, particularly with carbon and silicon, because they both have 4 valence electrons, and so it doesn't really do them much good to try to gain or lose. They're better off just trying to share them all. Now, there are some other ions out there without noble gas configurations, particularly the D and the P block metals, some of the lower ones. Many will form 2 pluses or 3 pluses. There's some 1 pluses or 4 pluses out there. Honestly, you need to spend some time with your ion sheet and try to become familiar with the patterns because we're going to need to know those. Now, monatomic ions, a lot of times the type of ion can be determined by looking at the number of valence electrons in the neutral atom. We've done this a few different ways where you're trying to figure out what it would take to get that noble gas configuration, which is going to help make the atom happy, and the way it makes the atom happy is by lowering the energy. Okay, again, the group 1s will have a 1 plus, the halogens will have a 1 minus, etc., etc. Atom is more stable with a full shell. 0 valence will lose electrons. These are going to be your cations. And 0 valence, just means it gives away all the electrons that are on the outer level. 8 valence, they will gain electrons. And a lot of these are your nonmetals. Okay, so there are some patterns to some of the types of atoms that form different cations or anions as well. Okay, cation is positive if the atom loses electrons. These are both group 2 or alkali earth metals, and so that's where they both have their 2 plus charge. An anion is negative if the atom gains electrons. Nitrogen needs 3 valence electrons, so that's why it will form a 3 minus ion. Fluorine ends in that P5 group, so if it has 2p to start with, it has 1, 2, 3, 4, 5, if it can get that 1 extra electron, it's happy, and then it has a 1 minus charge on it. Okay? Alright. Now, for naming ions, the cation always goes first. It's the element's name. We do add a Roman numeral if it can form more than one type of ion, and those are mostly D blocks, with the exception of zinc, which is always a 2 plus, and silver, which is always a 1 plus. The rest of the D blocks will need Roman numerals, I think, for the purposes of our class. It's what's called the stock system. There is another more traditional system out there. We're not going to learn that. Anions are negative. They go second in the formula, and again, we have this idea, well, not idea, but where we change the very ending to IDE. Okay, now if we have 2 different ions, we have to do what's called crossing over, meaning that the anion's charge becomes the cation's subscript, the cation's charge becomes the anion subscript, and we simplify. Okay, I know that sounds ugly. It's way easier than it actually sounds, so let's do some samples and we can try to make sense of it all. Okay, So if you were making a compound from aluminum and oxygen, the first thing you got to figure out is what are the two ions that you're dealing with. And aluminum has a 3 plus charge. It has 3 valence electrons. It wants to give those away. Oxygen has a 2 minus charge. It wants 2 more electrons, and then it's happy. Now when we say crossover, what has to happen is that the charge for oxygen becomes aluminum's subscript. So it's going to be Al2, okay, and then it's going to be O3. Now the reason why is that, remember, we want the whole thing equal to 0. So if I have 2 aluminums that each have a 3 plus, that gives me a total of 6 plus. For oxygen, I've got 3 that all have 2 minus, which gives me a total of 6 minus. Those two numbers have to cancel out. So the quick way is this whole crossing over idea. It's just a simpler way to do the math. You can do the math every time if you want to, but it's just a quicker way. Now magnesium and bromide. Also the name of this compound right here would be aluminum oxide. Okay. Now magnesium and bromine, again, you have a 2 plus charge on the magnesium, so essentially you're going to need 2 bromides to get to a total of 2 minus. And the quick way to do that is just that you're going to have Mg and 1. You don't have to write the 1, but the superscript over here is going to become the subscript, so it's going to be Br2. Or in other words, you need 2 bromides that each only have a 1 minus charge to cancel out the 2 plus charge of the magnesium. And the name of this one would be magnesium bromide. Okay? Alright, now let's pick these over here. Now if you look at copper, copper is one of those D blocks that has, excuse me, 2 options. One of the options for copper is copper 2. Bromide's a halogen, it's always going to be 1 minus. So if it's copper 2 and I do my crossing over, it's going to be Cu Br2. And the name of this compound right here would be copper 2 bromide. And that Roman numeral simply comes from the charge. That's it. If there's a Roman numeral, it's the charge on that ion. Okay, so it's just a matter of knowing if it has to be there or not. Oops, I want my pen back. Okay, now the other option for copper, and I put the 1, we normally if it's a 1 don't write the 1 in there, I just put it in there for emphasis. But this time it's copper 1 in bromide. So this formula would simply be CuBr, and this would be copper 1 bromide, which again simply tells us that that 1 indicates that this is copper 1 as opposed to copper 2. Alright, let's do some of the opposites. If you have iron 3 sulfide, this writing out the ion step isn't necessarily required, but particularly when you're first learning, it's really beneficial to do it because you get the extra practice and just kind of keeps everything and shows all your work and gets you organized. Now, if we have to now write the formula, we're going to crisscross these. And so this is going to end up being this will work. This is going to end up being there we go. Fe2S3. Okay, because we got to crisscross those in order to get there. Okay, cadmium oxide. Cadmium would be a 2 plus. Oxide is going to be a 2 minus. So if we crisscross them, we get CD2O2. However, we want to reduce that down to CDO. Okay, we don't want to leave multiple numbers, so to speak. Now potassium nitride is going to be, potassium is a 1 plus, nitride is N3 minus. So my formula here is K3N. Now tin 4 is telling me that the charge on the tin ion is 4 plus. Sulfide is 2 minus. So if I crisscross them, then to SN2, S4. Again, I want to reduce that down to SN, S2. Okay, SN, S2. Alright, no, those are all monatomic ions. Now we have to do some with, where's my moose here? There you go. polyatomics. Now the thing with the polyatomics, poly simply means many. Okay, so if you look at this, poly means more than one. So the cation or the anion can be a group of covalently bonded atoms instead of one atom. And you've got your list of polyatomics. Some you have to memorize, some you don't. Okay, most of them are oxyanions, which is a fancy way of saying that they contain oxygen. For example, you've got sulfate, which can be SO4 2-, sulfite SO3 2-. Some of them are very close. Again, some you're gonna get, and the others you're gonna have to commit to memory. So just learn them because they're not going away. We will do naming from now until May. So you're gonna have to learn them at some point. You might as well start now. Okay, so if you do a little bit of practice here, we just need to figure out what the names are of the ions that we're dealing with. And the thing is, whenever there is more than two types of atoms, you automatically are dealing with a polyatomic. Okay, so you're automatically dealing with a polyatomic. And this is going to be this first one. The two ions we're dealing with are potassium and nitrate. And so my name is simply potassium nitrate. Okay, now I always uncrisscross these just to show you the charges because they're going to be important on this one. This is going to be copper 2 because I know that hydroxide has a 1- charge, and since there were two of them, if I uncrisscross it, this has to be copper 2, which is going to be important because when I write my formula, it's got to be copper 2 hydroxide. Okay, because since copper can be copper 1 or copper 2, we have to write it this way. Now when you split this one up over here, you're going to have ammonium and bromide. Ammonium is one of the only positively charged or polyatomic cations, and then the name is simply ammonium bromide. Okay, ammonium bromide. And then last but not least, you've got calcium, which is a 2+, sulfate, which is a 2-. Now they're the same charge, so that's why they kind of cancel each other out. And so the name is simply going to be calcium. Oops, where did I go here? Sulfate. Okay, calcium sulfate. Alright, last but not least, here's going the opposite direction. I already gave you the ions here just to help you out a little bit. Potassium permanganate, here's the potassium ion and the permanganate ion. It's a 1-to-1, so my formula is simply sticking them together, NaMnO4. Now iron 2 chlorite, okay, is going to still be a little bit different here. If I crisscross it, I'm going to need 1 iron, but I need 2 of the entire chlorite. So when I need more than 1, I have to put the entire polyatomic in parentheses and put a 2 on the outside because I need 2 of those entire things. Because remember, here's the 2+, so I need 2 chlorites that have an overall 2- charge. Now ammonium acetate is about as ugly as it gets for us. It's a 1-to-1, so all I have to do is throw those two together. That's it. And then calcium carbonate, if I crisscross it, I would get Ca2, CO3-2. Well, those are going to reduce down to simply be CaCO3. And we will do lots and lots and lots of practice in this next class. So if you're not sure about it, don't worry about it. We'll get you there. Okay, good luck.